A faint shimmer drifts at the edge of the universe, so small and fragile that it almost disappears into the cosmic night. Yet the deeper the gaze travels, the more undeniable it becomes. Something is there, something ancient, something that has no right to exist. The discovery begins not with certainty but with a pulse, an almost accidental flicker in a sea of static. It's the kind of detail astronomers dismiss 1,000 times a day, the kind that dissolves upon closer inspection. But this time it refuses to dissolve. It waits, faint and stubborn, as though daring humanity to question what it truly understands about the birth of the cosmos. The universe stretches out like an endless ocean of darkness, a void so tremendous that even the brightest galaxies become nothing more than scattered sparks. Through this abyss, the James Webb Space Telescope peers back across time, sifting through ancient light, searching for the earliest whispers of creation. And then, amidst the swirling chaos of distant star fields, a strange glow appears, tiny, impossibly distant, shockingly old. It is not large enough to command attention, not bright enough to inspire immediate awe, yet it radiates a sense of quiet defiance. As though it stands there, whispering that the universe is not as young, simple, or predictable as humans once believed. Light from this object has been traveling toward us for more than 13 billion years, slipping through collapsing stars, drifting past collapsing galaxies, surviving the expansion of space itself. Every photon that reaches Webb's golden mirrors carries memories older than Earth, older than the Sun, older than the very idea of time as humans experience it. And in those memories lies a contradiction so severe that it shakes the foundations of modern science. Galaxies were not supposed to be small and structured at such an early cosmic moment. They were not supposed to form so quickly or remain so stable. Yet this one does. It stands like a fossil from a forgotten era, preserved with haunting clarity. As the telescope collects more data, the object sharpens into focus, and the sense of unease grows. Its faint light pulses with a rhythm that suggests mature stars, stars that should have taken hundreds of millions of years to form. Its compact shape hints at an organized structure, not the chaotic, turbulent mess expected in the young universe. It is as though nature skipped ahead in its own script, revealing a chapter that scientists never believed possible. And with each passing minute, the mystery deepens. Humanity has always clung to the illusion that the universe follows rules, a cosmic handbook of predictable cause and effect. But this discovery threatens to tear pages from that handbook, leaving only questions where answers once lived. How did such a tiny galaxy emerge in a universe barely out of infancy? What forces shaped it? What unknown processes allowed it to ignite so early in cosmic history? The possibilities swirl like dust in a beam of ancient starlight, each more unsettling than the last. The mind drifts to the primordial universe, a time of blistering heat, violent expansion, and raw quantum storms. A time when matter struggled to cool, when stars had not yet learned to burn, when gravity was still carving patterns into chaos. Imagining a delicate, coherent galaxy forming in such a brutal environment feels like imagining a fragile butterfly emerging from a volcanic eruption. Beautiful, impossible, contradictory. Yet here it is, shining softly across the void, refusing to obey the logic of its own age. Scientists trace its spectrum, hoping the lines will reveal an explanation, a mistake, a miscalculation, anything to restore order to their understanding. But instead, the lines confirm the truth. The object is real, ancient, and undeniably structured. It is not an illusion. It is not a glitch. It is a message from the dawn of time, one that humanity was never prepared to receive. The more evidence accumulates, the more the mystery transforms from an anomaly into a revelation. Across observatories and research centers, whispers turn into debates, and debates turn into heated discussions. Some insist it challenges the timeline of the Big Bang. Others argue it reveals unknown physics. A few dare to propose that it hints at something even more profound, a hidden aspect of the universe, one that has been at work long before humanity had eyes to see it. But regardless of the interpretation, one truth becomes inescapable: the cosmos is not finished surprising us. This tiny galaxy becomes a symbol of cosmic rebellion, a lone spark defying the vast machinery of time. Its presence forces scientists to confront the unsettling possibility that the early universe was more complex, more turbulent, and far stranger than anyone imagined. Perhaps the rules were different. Perhaps unknown forces shaped creation in ways we're only beginning to glimpse. Or perhaps human understanding is still painfully incomplete, a childlike attempt to comprehend a universe that operates on scales of mystery beyond imagination. As the documentary's journey begins, this discovery stands at the threshold, silent, glowing, enigmatic. It beckons us forward, urging us to follow the trail of contradictions it leaves behind. Every unanswered question becomes an invitation. Every strange detail becomes a doorway. And as the camera drifts deeper into the ancient light, one thing becomes clear. Humanity has stumbled upon something bigger than a tiny galaxy. It has stumbled upon a cosmic secret waiting billions of years to be found. And the universe, vast and unbothered, watches as we try to understand the impossible. A soft, ghost-like glow lingers at the very edge of detectability, as though the universe itself is whispering a secret too delicate for human senses. This is the tiny galaxy, so faint, so impossibly small, that it nearly slips through the cracks of cosmic perception. It does not blaze with the confident brightness of giant spirals or starburst formations. Instead, it flickers like a dying ember preserved across 13 billion years, a fragile, trembling artifact from a time when the universe itself was still learning how to breathe. And yet, within this faint smudge lies a contradiction powerful enough to challenge every model, every assumption, every law of formation that scientists have trusted for decades. The first thing that startles researchers is its size. This galaxy is not just small, it is minuscule, almost absurdly tiny compared to the grand, sweeping structures familiar to modern astronomy. If the Milky Way were stretched across an entire continent, this galaxy would be the size of a single street block. A microscopic island of light swallowed by an ocean of primordial darkness. Its diameter is so compact that it seems less like a galaxy and more like a tightly clenched fist of ancient stars, gathered together with a determination that defies its cosmic environment. But its size is not the only impossible quality. What truly sends shivers through the scientific community is its age. This small galaxy appears older than logic allows, an object brimming with mature characteristics in a universe that should have barely cooled from its initial explosion. The early cosmos was chaotic, violent, and unwelcoming, a domain of swirling plasma and brutal gravitational battles. Galaxies were supposed to be clumpy, misshapen, struggling against turbulence. And yet this one glows with a quiet, inexplicable order, as though it has already lived through epochs that should not have existed. Its light carries a strange steadiness, a calmness that contradicts the expected violence of its era. It emits the signature of stars that seem well-formed, composed, and old enough to suggest generations of stellar evolution, something cosmology insists should not be possible so early. These stars should not have had enough time to fuse hydrogen into heavier elements, explode as supernovae, and seed the galaxy with complex chemistry. Yet their glow hints at exactly that. It is as though the galaxy matured at a pace far exceeding anything the universe should have allowed. When astronomers examine its brightness profile, they notice something even more troubling. This tiny galaxy is dense, shockingly dense. Its stars appear tightly packed, almost pressed together by forces that seem too efficient, too organized for such an early cosmic stage. Instead of scattering loosely, they sit clustered like jewels set into a compact crown of ancient light. The structure feels deliberate, almost architectural, as though shaped by an unseen hand or an unknown mechanism of early cosmic formation. The contrast is as disturbing as it is mesmerizing. The galaxy's size suggests weakness, fragility, transience. Yet its density and maturity radiate a sense of ancient strength, as though it carries memories older than the universe's accepted timeline. This is a paradox wrapped in starlight, a contradiction too precise to ignore. The faintness of the object only deepens its mystery. To detect it at all requires immense sensitivity and an almost poetic harmony of precise conditions. Its photons, stretched across billions of years, have survived collisions, distortions, cosmic inflation, and the suffocating silence of space. Each particle of light that hits Webb's mirrors is a survivor of unimaginable distance and time. And within those particles lies a whisper: this galaxy should not be here. Astronomers analyze its shape, expecting chaos, asymmetry, or violent distortions typical of young galaxies. Instead, they find hints of smoothness, organization, and surprising coherence. It is not a sprawling cluster but a tiny, tightened knot of stars, held together in a way that defies the expected physics of its age. The universe at that stage was not supposed to allow such things. Gravity should have been too weak, matter too hot, the cosmic web too underdeveloped. But this little structure decided otherwise. Some researchers describe it as a cosmic fossil, a rare, improbable relic that somehow survived against the odds. Others call it a glitch, a mistake in the universe's early programming, something that slipped through the cracks of natural law. But even these metaphors fall short. This galaxy is not merely unusual, it is a direct challenge to the timeline of cosmic evolution itself. Visualizing it feels like imagining a candle burning brightly during a thunderstorm that should have extinguished it instantly. The storm was too wild, too young, too powerful. Yet the candle remains lit. What? Oh. What shielded it? What allowed it to form such mature stars so early, so fast, so efficiently? As JWST gathers more data, the picture becomes even stranger. The galaxy's internal chemistry, though faint, hints at elements that should not exist yet. Its stellar distribution suggests processes that demand more time than the universe had at the moment of its birth. Every measurement seems to push scientists further away from comfort and closer into the unknown. And then there is the emotional weight of the discovery. Astronomy is built on patterns, on predictability, on the confidence that light reveals truth in a linear, trustworthy way. But this little galaxy feels like a rebel, a cosmic protest against humanity's assumptions. Its existence whispers that the early universe may have been more complex, more fertile, more enigmatic than anyone imagined. Perhaps galaxies formed faster than expected. Perhaps certain pockets of matter collapsed with impossible speed. Or perhaps, though the thought chills even the boldest cosmologists, our understanding of time, gravity, or cosmic evolution is deeply incomplete. The more scientists stare at this tiny galaxy, the more it stares back, unblinking, unapologetic. It stands as a contradiction carved into the fabric of the universe, a reminder that reality is not obligated to obey human expectations. And as the faint glow from that impossible structure continues its journey across the cosmos, it carries with it a single haunting message. The universe is still full of secrets we are only beginning to uncover. For a moment, imagine drifting through the cold, silent reaches of space, where darkness stretches endlessly and stars shimmer like distant memories. In this infinite void floats one of humanity's greatest achievements, a machine so precise, so powerful, that it can reach back across cosmic time itself. The James Webb Space Telescope hangs suspended like a vast, golden eye, its mirrors glinting softly as they drink in the ancient light of forgotten eras. It is not simply a telescope, it is a time machine, a cosmic storyteller, capable of revealing chapters of the universe that remain sealed for billions of years. And it is this extraordinary instrument that first uncovered the tiny, impossible galaxy that should never have existed. Webb's journey to the stars began long before its mirrors ever tasted sunlight. For decades, engineers, scientists, and dreamers designed it with almost obsessive care. Every bolt, every sensor, every thin sheet of gold was chosen with one purpose in mind: to unlock the secrets of the early universe. The Hubble Space Telescope had shown us wonders, nebulae shaped like ghostly wings, galaxies dancing in slow cosmic ballets, but Webb was built to go even deeper, to see the universe not as it is, but as it once was. Its infrared eyes allow it to pierce through cosmic dust, to catch whispers of light so stretched and weakened that only the most sensitive instruments could detect them. Webb does not simply observe stars, it listens to the fading echoes of creation itself. When its massive sunshield unfolded in the vacuum of space, it resembled a silver flower blooming in the darkness. Layer after layer stretched open, forming a protective cocoon that allowed the telescope to cool to unimaginably low temperatures. It had to be cold, almost painfully cold, because warmth creates noise, and noise drowns out the fragile signals of ancient galaxies. Webb was built to hear the quietest voices in the cosmos, voices so faint that they had been ignored, buried, or lost for billions of years. Only in near-perfect silence could their stories be heard. Its primary mirror, a masterpiece of engineering, is composed of 18 hexagonal segments, each one coated with pure gold to maximize the reflection of infrared light. Together, they form a vast, shimmering dish that captures cosmic echoes across unimaginable distances. Light that began its journey before planets formed, before stars matured, before time itself felt stable, falls into Webb's mirrors like grains of sand slipping through an hourglass. And with each captured photon, the telescope reconstructs lost epochs, revealing the universe's earliest attempts at creation. Webb sees the universe as it existed just a few 100 million years after the Big Bang. To put that into perspective, if the universe's entire history were compressed into a single 24-hour day, Webb observes events that happened within the first few minutes. It peers through layers of cosmic fog and unravels the tangled threads of early formation. Galaxies, once thought to need billions of years to evolve, appear suddenly with structure, with order, with complexity. It is this ability, to witness creation in its infancy, that makes Webb unlike any telescope before it. Yet for all its complexity, Webb feels strangely fragile. It orbits far beyond the reach of human hands, a lonely guardian drifting at the second Lagrange point, balanced in a gravitational dance between Earth and Sunday. If anything were to go wrong, there would be no rescue mission. Everything had to work on the first try. Every mechanism had to unfold flawlessly. The universe offered no second chances. And somehow, miraculously, everything did work. The telescope came alive like a slumbering titan lifting its head, its golden eyes opening to stare into eternity. Once operational, Webb began its hunt for the earliest galaxies. It scanned patches of night sky so small that they looked empty to the naked eye, voids where nothing seemed to exist. But Webb knew better. These empty regions were windows into the past, portals to moments when the universe was young, raw, and experimenting with the first sparks of structure. It was during one of these surveys that Webb detected a faint glow, a tiny spark of light barely distinguishable from the cosmic background. It was so delicate, so ghost-like that older telescopes would have dismissed it as noise. But to Webb, that faint signal was a message, a clue, an invitation to dig deeper. The deeper the telescope looked, the stranger the object became. Its distance placed it firmly in the universe's earliest era. Its size was shockingly small. Its stars were unexpectedly mature. Webb traced its composition through its spectral signature, the chemical fingerprints etched in the light it emitted. Those fingerprints whispered secrets of formation, of processes that should not have been possible so early in cosmic evolution. Webb had uncovered something that violated expectations in almost every measurable way. And as scientists processed the data, a quiet thrill rippled through the astronomical community. Webb had fulfilled its purpose, not only to confirm theories but to challenge them. To reveal not just the expected but the unimaginable. Its instruments were so sensitive that they could detect the tiniest deviations in ancient light, deviations that exposed cosmic anomalies like the mysterious tiny galaxy now capturing global attention. This anomaly became a symbol of Webb's power, a testament to how dramatically the telescope could rewrite humanity's understanding of the universe. For researchers, Webb's images felt like revelations. They were not just photographs, they were windows into alternate versions of history, frozen moments where the universe seemed to experiment with ideas that defied logic. Each pixel of data carried weight, significance, and the potential to alter scientific doctrine. The telescope acted like a cosmic detective, gathering clues scattered across billions of light years, constructing a narrative of creation more complex and more beautiful than anyone dared imagine. And yet, with every discovery, Webb also raised deeper questions. How many ancient galaxies had been missed because humanity lacked the technology to see them? What other anomalies lingered in the darkness, waiting for a telescope powerful enough to reveal them? If something as small and mature as this galaxy could exist so early, what else might be hiding at the dawn of time? Webb continues to scan the sky, its golden mirrors glowing faintly as it collects the final remnants of ancient light. It listens to the universe with a patience only a machine can possess, extracting secrets one photon at a time. It does not judge or interpret, it simply gathers, reveals, and illuminates. But the questions it raises transform human understanding forever. The James Webb Space Telescope is more than a scientific instrument. It is a reminder that the universe is still full of mysteries, that humanity's greatest discoveries may lie not in what we expect, but in what surprises us. And with each new observation, Webb pushes the boundary between known and unknown further into the cosmic dark. In the beginning, long before Earth formed, long before the sun ignited, long before atoms settled into familiar patterns, the universe followed a set of rules, ancient, invisible, and uncompromising. These rules shaped everything: the birth of stars, the clustering of matter, the flow of gravity, and the evolution of galaxies. Scientists call this framework the standard cosmological model, a cosmic rulebook built from decades of observations, equations, and evidence. It has guided humanity's understanding of the universe like a sacred map. But to understand why the tiny galaxy discovered by Webb is so shocking, we must first revisit what the universe was supposed to look like in its earliest moments according to this rulebook. And when we open its pages, the contradiction becomes impossible to ignore. The story of galaxy formation begins roughly 300,000 years after the Big Bang, when the universe finally cooled enough for atoms to form. Before that moment, it was a blinding storm of plasma and radiation, a turbulent sea where light could not travel freely. When the first atoms appeared, the cosmic fog lifted. This era is known as recombination, the moment the universe became transparent. But even then, galaxies did not exist. Stars did not exist. The universe was dark, silent, and almost empty. Gravity had only just begun to tug at scattered pockets of matter, and the cosmic web, the vast structure of filaments and voids we see today, was merely a faint outline. Over millions of years, Those pockets of matter slowly gathered together under the pull of gravity. But the process was painfully slow. The early universe was too hot, too energetic, too chaotic for delicate structures to form. Protons and electrons drifted through the void like scattered seeds waiting for soil that did not yet exist. Tiny fluctuations in density created the first gravitational wells, pulling matter inward, forming clouds that would eventually collapse into stars. But according to the cosmic rulebook, this collapse required time, hundreds of millions of years. Galaxies could not simply appear fully formed. They had to be built piece by piece, atom by atom, generation by generation. When these first stars finally ignited, they were monstrous, giant, unstable, extremely hot, and short-lived. Scientists call them population 3 stars, and although they have never been directly observed, their existence is fundamental to the story of galaxy formation. These early stars lived fast and died explosively, forging the first heavy elements in their fiery deaths. Only after these stars died could new generations form. Population 2 stars enriched with metals, capable of clustering into larger and more stable galaxies. This enrichment process in theory took vast amounts of time. It required cycles of birth and destruction, explosions scattering material, clouds reforming, and gravity pulling everything together again. This is why early galaxies were expected to be chaotic, irregular, and extremely young. They should have contained mostly primordial gases, hydrogen and helium, and almost no heavy elements. Their shapes should have been messy, their stars unpredictable, their chemistry primitive. And because the early universe was still settling into its cosmic architecture, galaxies should have been relatively large and clumpy, not small and tightly structured. This was the fundamental expectation. Early galaxies should look immature, turbulent, and unstable. But the tiny galaxy revealed by Webb is none of these things. Instead of chaos, it displays coherence. Instead of immature stars, it shows signs of maturity. Instead of primitive chemistry, it hints at elements that should have taken generations of stellar evolution to produce. According to the cosmic rulebook, this should not have been possible. The universe, at the time this galaxy existed, was too young, too raw, to allow such organization. Something does not add up. Something is violating the rules. To understand the severity of this violation, imagine the universe as a grand construction site. Gravity is the builder, slowly assembling stars into clusters, clusters into galaxies, and galaxies into larger structures. In the early stages of construction, everything should be messy. Beams unaligned, walls not yet formed, foundations unstable. But Webb has discovered what appears to be a fully furnished room in a building that hasn't even been erected yet. It is as though the universe skipped an entire stage of development and jumped straight into complexity. The standard model insists that galaxy formation is hierarchical. Large galaxies form through the merging of smaller ones. Small galaxies are the building blocks. But even those small building blocks should have taken time to form and evolve. The tiny galaxy in question seems not just too early but too complete. Its stars seem too old, its density too high, its structure too refined. It is a violation not of one rule but of many: gravity, chemistry, star formation, cosmic chronology. This raises a profound question. If one galaxy can break the rules, how many others might exist? How many examples have we missed because our instruments were not powerful enough to detect them? And if galaxies like this one are common rather than rare, then the entire story of cosmic evolution, the timeline, the processes, the physics, may need to be rewritten. The cosmic rulebook has served humanity well, predicting cosmic microwave background patterns, galaxy distributions, and the expansion of the universe. But now a single, quiet, tiny galaxy stands in defiance of its pages. It forces scientists to confront a possibility that is both exhilarating and terrifying. The rulebook might be incomplete. And if the rules of galaxy formation are not what we thought, then our understanding of the universe's earliest chapters may be nothing more than a comforting myth, one that Webb is now tearing apart, one impossible discovery at a time. The early universe was a place no human imagination can fully capture, a realm of relentless energy, violent transformation, and raw, unshaped possibility. It was not a quiet, cooling cosmos strewn with elegant galaxies and gentle starlight. It was a young, ferocious beast, roaring with expanding space, swirling with plasma, and trembling under the weight of forces still settling into their identities. Time itself felt unstable, rushing forward in chaotic bursts, stretching matter, bending light, and sculpting reality with a brutality that defies description. In this tempestuous environment, nothing delicate was supposed to survive, let alone form. And yet the mysterious tiny galaxy discovered by Webb appears to have done exactly that, as though it emerged in the middle of a cosmic storm that should have torn it apart instantly. To understand why this discovery seems impossible, we must return to the first few 100 million years, an era known as the Cosmic Dawn. After the Big Bang, the universe expanded at an unimaginable rate, cooling from a furnace hotter than any star to a vast, simmering sea of particles. Gravity had just begun its eternal work, pulling matter into clumps so small they were barely more than whispers in the darkness. There were no galaxies, no stars, no planets, only scattered clouds of hydrogen and helium drifting through a void still echoing with the universe's explosive birth. Heat was everywhere, suppressing the collapse of matter, fighting against gravity's attempt to create structure. Every step toward complexity was met with resistance. Every attempt at formation faced a universe still too wild, too young, too hot to cooperate. And yet, even in these early moments, the seeds of galaxies were forming. But those seeds were fragile, tiny regions of slightly higher density that gravity slowly tightened. Slowly was the key. In a universe ruled by violent expansion and extreme temperatures, nothing happened quickly. The first stars took hundreds of millions of years to ignite. Galaxies, even crude ones, needed more time. The cosmos was a chaotic battlefield of radiation and matter, and only after long ages of cooling could anything delicate take shape. This is why the early universe was not ready for stability, not ready for structure. Certainly not ready for a miniature organized galaxy that looked like it had skipped ahead in evolution. Scientists describe these early times as a cosmic dark age, not because space was truly black, radiation was everywhere, but because light from stars did not yet exist. Without stars, the universe was like an ink-filled ocean, dense, hot, and turbulent. The energy left over from the Big Bang flooded the cosmos, preventing atoms from settling into predictable patterns. Matter fluttered like sparks in a raging fire, ripped apart before it could gather. Any attempt at forming stars would have been smothered by surrounding heat. Any attempt at forming galaxies would have been shredded by expanding space. The universe, in those early moments, was simply not gentle enough to allow order. This is why the discovery of a tiny, mature-looking galaxy existing so early is so startling. It is not just unlikely, it is nearly impossible based on the conditions known to exist at the time. It is as though the cosmic environment took a break from chaos, paused its turbulence, and quietly allowed an island of stability to emerge. But nothing in the early universe suggests such a pause ever occurred. If anything, the universe was at its most violent during this period, colliding particles, surging energies, and a constant battle between cooling and expansion. Galaxies at this stage should have been messy, lopsided, and incomplete, formed from scattered clusters violently smashing together. Their stars should have been few, primitive, and blazing with short lives. Their chemistry should have been simple, almost childlike. But the tiny galaxy detected by Webb doesn't behave like something forged in the fire of a young universe. It looks like something shaped in a place of patience, stability, and slow growth, a place that should not have existed yet. Imagine a delicate flower blooming during a raging volcanic eruption. That is what this galaxy represents. A quiet structure blossoming in a universe that seemed violently opposed to its existence. The cosmic pressure, the intense radiation, the relentless expansion, all of it should have crushed or dispersed any attempt at forming a coherent galaxy. But somehow this tiny structure formed quickly, efficiently, and with surprising maturity. The contradiction deepens when scientists consider the timeline. The tiny galaxy appears to have formed within a few 100 million years after the Big Bang, an eye blink in cosmic terms. But according to established physics, there simply wasn't enough time for gas to collapse, stars to form, stars to die, heavy elements to scatter, and new stars to form again. This required cycle of destruction and rebirth, the foundation of mature galaxies, could not possibly have occurred so fast. And yet the chemical signatures suggest otherwise. The early universe was too hot, too crowded, too prone to cosmic violence. It wasn't ready for complex structure. It wasn't ready for calmness. It wasn't ready for galaxies that behaved like they belonged to a much later era. This is why the discovery feels like a rupture, a tear in the carefully constructed story scientists believed about how the universe built itself. The more astronomers examine the data, the more the contradiction gnaws at them. The early universe should have been a furnace of instability, yet here lies a fragile, coherent system surviving against all odds. If the universe wasn't ready for this galaxy, then how did it appear? What hidden forces allowed it to form? What unknown processes worked behind the scenes during cosmic dawn? The tiny galaxy stands as evidence that the universe may have evolved differently than thought, faster than assumed, or under conditions no model has yet captured. It is a reminder that the cosmos is not required to match human expectations. It does not obey theoretical boundaries. It simply exists in all its mystery. And in that mystery, this tiny galaxy shines, a soft light in a violent era, a defiant anomaly in a universe that should have crushed it. Its presence challenges everything we think we know, inviting us deeper into the untamed, unpredictable truth of the early cosmos. The anomaly first appeared as nothing more than a faint, almost ignorable flicker buried deep within a flood of cosmic data, one of thousands of tiny signals that astronomers scan through every day. At first glance, it looked like noise, the sort of stray point of light that is usually dismissed with a single click. But something about this signal refused to be dismissed. It lingered, holding its place against the background darkness with a strange persistence, as if it were waiting for someone to notice. And when the first astronomer paused long enough to look closer, the entire trajectory of the investigation changed. The moment itself was quiet, almost mundane. A researcher sat in a dimly lit lab, late into the night, surrounded by screens glowing with ancient cosmic light. Eyes tired, mind overloaded, they scanned through newly received Webb data, ordinary work, repetitive work, yet work that occasionally revealed the extraordinary. A faint object caught their attention. It didn't fit the typical pattern of early universe noise. It wasn't scattered or inconsistent. It was steady, delicate, perfectly centered. That alone was strange. Signals at that distance are rarely cooperative. They flicker, fade, deform. But this one held its shape like a whisper refusing to vanish. Curiosity took over. With a few keystrokes, the astronomer enhanced the signal, refined the image, and filtered out the surrounding cosmic clutter. What emerged was small, dim, and unsettlingly clear, a tiny patch of concentrated light barely larger than a pixel. It didn't flare with the brightness of a quasar or the distorted smear of a lensed galaxy. It glowed with quiet conviction, precise and subtle. That precision was the first sign that something was off. Objects from the early universe are supposed to be messy, chaotic, irregular. This faint smudge looked almost intentional. The initial reaction was confusion. The astronomer leaned back, blinked, leaned forward again. Checked the coordinates. Checked the redshift estimate. Checked for instrumental errors. Everything seemed normal. No glitches. No misreads. No calibration issues. The data appeared genuine. But that only deepened the unease. How could something this small, this old-looking, exist at such an impossible distance? A message was sent to a colleague. Then another. Soon a small group gathered around a shared screen, bathed in the soft glow of ancient light. Each one stared at the tiny object with expressions that shifted from curiosity to disbelief. The silence in the room grew heavier with every confirmation. No one wanted to say it aloud yet, but they all sensed it. Something was wrong. Something didn't match the rules. Something shouldn't be there. At this stage, caution was essential. Astronomers have been fooled before by reflections, lensing artifacts, distant stars masquerading as galaxies, and even cosmic rays striking a sensor at the wrong moment. So the team approached the anomaly with meticulous skepticism. They ran diagnostics, cross-referenced exposures, and repeated the analysis using different filters. The object remained. It didn't blink out. It didn't shift. It didn't distort. It stayed anchored in the same spot, an ancient ember glowing at the edge of the observable universe. The debates began immediately. Was it a star? No, the signature was too diffuse. Was it a cluster? Too compact. Was it lensing? No foreground objects aligned with it. Could it be a sensor artifact? Highly unlikely after so many checks. With each eliminated possibility, the tension in the room grew sharper. They needed more data, clearer spectroscopic information, deeper imaging, more validation. But even without that, the signal was already unsettling enough to demand attention. The first round of spectral data finally came in, faint but decipherable. And with it came the second shock. The redshift was enormous, far higher than expected. This object existed when the universe was only a fraction of its current age. Its light had been traveling toward Earth since long before the Milky Way formed. Yet instead of being primitive, shapeless, or chaotic, the signal suggested structure, density, maturity. It hinted at stars too developed for such an early time. A pulse of excitement and fear ran through the researchers. They were now staring at something that contradicted fundamental assumptions about cosmic evolution. This wasn't just an unusual galaxy, it was a direct challenge to the timeline itself. What they had discovered might require new physics, new models, maybe even a rethinking of the cosmic origin story. One astronomer leaned forward, whispering the words that would soon echo across the entire investigation. If this is real, it changes everything. But even as the implications sank in, caution held them back from drawing conclusions. Could the signal be misinterpreted? Could an unknown distortion mimic maturity? Could the redshift estimate be wrong? Every possibility had to be explored. And yet, beneath the careful skepticism, a quiet thrill spread through the team. They sensed they were on the verge of something monumental. Night turned into morning as they worked. Emails flew across continents. Calls were made. Teams in other observatories were contacted for independent verification. The anomaly was no longer just a faint flicker in a dataset. It had become an urgent mystery, a potential discovery that demanded the attention of the global astronomical community. But even before the confirmation came, one thing was already clear. This tiny, fragile object, this stubborn little spark in the darkness, was not going away. It had stepped out from the cosmic background with a message older than time, and now humanity was compelled to listen. The first suspicious signal had awakened a quiet storm of curiosity, doubt, and wonder, and scientists were preparing to dive deeper into the unknown. The telescope shifted its gaze with the slow, deliberate precision of a hunter locking onto its prey. In the vast emptiness of space, where distances stretched beyond comprehension, JWST maneuvered with quiet elegance, its golden mirrors tilting ever so slightly to center the faint anomaly within its field of view. The tiny, impossible galaxy that had appeared as nothing more than a suspicious flicker was now about to face the unblinking scrutiny of humanity's most powerful eye. The moment was tense, electric, like a spotlight narrowing onto a single performer on a dark, cosmic stage. As the telescope prepared to zoom in, the team on Earth was struck by a palpable stillness. Screens dimmed. Instruments calibrated. Sensors came alive with gentle pings of readiness. Engineers, astronomers, and analysts gathered around datasets streaming in real time, each one aware that the next few hours could change everything. No one spoke unnecessarily. No one wanted to break the fragile bubble of anticipation. This was no longer routine observation. This was pursuit. They were about to track an object that didn't fit into the known universe's chronology, a structure that defied the rules they had spent decades perfecting. Webb began its deep zoom layering exposures, each one revealing a little more of the ancient message carried across billions of years. The first close-up was still faint, just a slightly clearer smudge on an endless backdrop of darkness, but even that was enough to stir unease. The shape was too compact, too orderly, too persistent. Early galaxies were supposed to be irregular, chaotic storms of gas and dust. This one looked condensed, self-assured, gathered tightly as though holding a secret within its tiny frame. The telescope's NRCam instrument sharpened the view further. More photons gathered. More noise filtered out. Slowly, the galaxy's edges emerged like a ghost stepping forward out of the fog. The faint smudge now hinted at a real structure, small, dense, and unmistakably present. Silence tightened in the control rooms. The faint patch wasn't dissolving into nothingness like an artifact would. Instead, it was becoming clearer, more distinct, more alarming. It was during the next stage, the deep spectral zoom, that the emotional weight hit the scientific team. Webb switched to its spectroscopic instruments, splitting the galaxy's ancient light into its elemental fingerprints. Each line in the spectrum told a story: temperature, composition, velocity, age. These lines were the universe's own handwriting, and Webb was reading it with the precision of a master decoder. The raw data began pouring in lines of numbers that would soon be translated into cosmic truths. Analysts stared, blinked, zoomed in. Then the murmur started. The spectral lines indicated something that should have been impossible. Features consistent with mature stars, stars that had gone through multiple cycles of formation and destruction. In the early universe, star populations should have been young, hot, and primitive. Yet this tiny galaxy seemed to hold signatures of heavier elements, subtle but unmistakable, as though it had lived an entire lifetime before it had any right to. This was where the thrill clashed violently with fear. One researcher whispered, "How can it have metals? How can it have this structure?" Another shook their head. At that age, it shouldn't. Webb zoomed deeper. Each new magnification peeled away another layer of mystery. The galaxy appeared like a compact knot of starlight, not stretched or distorted, not chaotic, but compressed with a uniformity that signaled coherent formation. It was as if gravity had sculpted it with unusual efficiency, ignoring the turbulence that should have dominated the era. The more magnification increased, the more the galaxy's stubborn clarity felt like an act of defiance. But something else caught the scientists off guard. The object's light profile implied density far greater than expected. The galaxy wasn't just small, it was intensely concentrated. That density suggested star formation rates far above what the early universe should have supported. It was as though this galaxy had collapsed and assembled with a speed and precision unmatched by any known model. As Webb locked onto this cosmic anomaly with its full observational power, emotions on Earth reached a fever pitch. Awe collided with dread. Excitement tangled with disbelief. It felt like peering into a forbidden page of the universe's diary, one written long before humanity had the right to read it. Still, the deeper the zoom went, the more unsettling the details became. The galaxy's profile didn't match any cataloged structure. Its color distribution implied older stellar populations. Its brightness ratio contradicted expected mass estimates. Every new frame brought more contradictions, more questions, more evidence that this was not a glitch, not a misinterpretation, but something profoundly real. By now, the scientific team felt it in their bones. This anomaly was not just unusual. It was unprecedented. The telescope continued gathering data as though nothing extraordinary were happening, its mechanical heart silent, its golden eye unblinking. But to the humans watching, this was a confrontation with something that should not exist. The more Webb zoomed in, the clearer the truth became. They were staring at a relic from a chapter of the universe that didn't match the story they thought they understood. It was the kind of discovery that could unravel theories, challenge timelines, and rewrite the origins of cosmic structure. And as the final, crisp images loaded, showing that tiny galaxy with impossible clarity, the room fell into breathless stillness. The universe had hidden this miracle for billions of years. Now JWST had finally seen it, and it was ready to reveal the impossible. The deeper the astronomers examined the data pouring in from JWST, the more an unsettling truth began to crystallize. The tiny galaxy was not just unusual. It was not merely compact or unexpectedly dense. It was something far more disturbing, something that violated the universe's own timeline. According to every known model of cosmic evolution, the universe at that point was still a newborn, barely stepping out of its chaotic infancy. Yet the light encoded within this tiny galaxy whispered a paradox that felt impossible to ignore. This galaxy appeared older than the universe should have allowed. To grasp the scale of this contradiction, imagine standing in front of a child who somehow possesses the memories, scars, and wisdom of an ancient elder. A being that should be just beginning life instead carries the unmistakable signs of long, complex experience. This galaxy, like that child, embodied an age far beyond its rightful place in time. It glowed not with the raw, chaotic energy of early cosmic youth but with the calm, measured radiance of something that had already lived through eras of transformation. The earliest universe was supposed to be a place without seasoned stars, without mature structures, without the heavy elements forged through cycles of stellar birth and destruction. Everything was young, untested, unrefined, chaotic. Galaxies could begin forming, yes, but they should have been messy and incomplete. Their stars should have been primordial, composed almost entirely of hydrogen and helium. They should not have displayed the signatures of multiple generations of stars. And yet here stood this tiny galaxy, emitting a spectrum that screamed of age, complexity, and history. The first clue came from the spectral redshift. The distance was staggering, so far back in time that the universe was still in its early dawn. But the chemical fingerprints embedded in the galaxy's light told another story. There were hints of metals, iron, oxygen, carbon, elements that required earlier stars to have lived, burned, and exploded. Those explosions would have needed time, cycles, and repeated generations. But in this era, there should have been no time for any of that. The scientists stared at the data in disbelief, each line of the spectrum challenging what they believed to be immutable truths. This was not the signature of a young, freshly formed galaxy. This was the echo of something that had already undergone sophisticated evolution. It was a paradox. A contradiction so sharp it cut through the foundations of cosmology. If the galaxy was truly this old, then the universe must have formed structures far more quickly than any current model allowed. Theories of hierarchical growth, where galaxies slowly merge and evolve over vast timelines, would need revision. The rules that bound the early cosmos, the pacing of star formation, the cooling of gas, the gravitational collapse of matter, all of it might be wrong or at least incomplete. Some astronomers tried to rationalize the data. Perhaps the readings were misinterpreted. Maybe gravitational lensing had distorted the signatures. Maybe the galaxy was not as old as it seemed, just masquerading as mature due to unusual environmental factors. But the more they examined the data, the harder it became to sustain those explanations. The galaxy's structure was compact and efficient, as though it had evolved in a protected pocket of spacetime. Its luminosity profile matched those of galaxies billions of years older. Its chemical distribution suggested processes that required astronomical time spans. Every new analysis deepened the existential discomfort. This galaxy was behaving like it belonged to a much later chapter in the universe's story. And so the researchers began to ask the forbidden question: could their understanding of time itself be flawed? For decades, cosmic chronology has been built on careful measurements of expansion rates, background radiation, and gravitational behavior. But what if a hidden variable existed? What if time flowed differently in certain pockets of the early universe? Or what if matter clumped more rapidly under exotic conditions that standard models had never accounted for? It was a chilling thought, one that stretched scientific imagination toward realms once considered fantasy. Some theorists proposed that early dark matter could have accelerated structure formation in ways not yet understood. Others speculated about unknown particle physics at play. A few whispered about the possibility of alternate cosmic pathways, branching timelines or regions where the laws of physics subtly deviated. These ideas were bold, unsettling, and controversial, but the galaxy demanded explanations as extraordinary as its existence. Even more unsettling was the implication that this tiny object might not be unique. If one galaxy had formed far too quickly, others might have as well, hidden in the cosmic shadows, waiting for JWST's gaze. The universe might be filled with these ancient-looking anomalies, like archaeological artifacts buried deep within spacetime, hinting at events no current theory can explain. As researchers absorbed the magnitude of the paradox, a quiet dread settled among them. This wasn't just a question of a single galaxy. It was a question of the universe's own beginning, its rules, its chronology, its very nature. Because if this galaxy truly appeared older than the universe should allow, then the story of cosmic evolution is not what we thought it was. It means the universe began differently. It evolved differently. And perhaps, though the idea trembles on the edge of scientific imagination, it has been hiding in ancient truth since the dawn of time. This tiny, impossible galaxy is more than an anomaly. It is a challenge, a riddle, a silent whisper from the universe's earliest moments, insisting that the past is far more mysterious than anyone ever imagined. From the moment JWST began collecting the spectral data of the tiny, impossible galaxy, astronomers knew they were staring into a window far older and stranger than expected. The light that reached Webb's golden mirrors had been stretched so dramatically by the expansion of the universe that it was no longer visible to the human eye. It arrived as ancient infrared whispers, faint, fragile, but filled with secrets written in the language of chemistry. To decode those secrets, scientists split the light into its spectral components, revealing thin, glowing lines that acted like cosmic fingerprints. And what those fingerprints showed was nothing short of astonishing. Spectral lines are the universe's DNA. Every atom, every molecule, every element absorbs and emits light at specific wavelengths, etching unique signatures into the spectrum. By reading these patterns, astronomers can determine what a galaxy is made of, how hot its stars burn, how quickly its gases churn, and how old its structures might be. Early galaxies should contain only the simplest signatures, pure hydrogen, pure helium, because the universe had not yet forged heavier elements. The first stars needed to live their entire life cycles before producing metals. Those stars had not existed long enough at the time this tiny galaxy supposedly formed. And yet, when the spectrum of the anomaly appeared on screen, the scientists froze. There were traces of heavier elements, subtle but unmistakable. Oxygen, carbon, possibly even early hints of iron. These elements can only be created through nuclear fusion inside stars and then scattered into space when those stars explode as supernovae. For such metals to be present in this minuscule structure, a full generation, or more, of stars must have lived and died. But the timeline didn't allow it. The universe during this epoch should have been dominated by massive, short-lived population 3 stars that were just beginning to ignite. Heavy elements should have been nearly non-existent. But the galaxy's light told a different story. The spectral peaks danced across the screen like ghostly signatures, revealing a chemical richness far too advanced for the galaxy's supposed age. Some wavelengths suggested cooler, older stars. Others hinted at a surprising density of starlight, the kind seen in galaxies that have already undergone multiple rounds of stellar evolution. The chemistry did not belong to a newborn structure. It belonged to something experienced, something matured, something impossibly evolved. The more the team studied the spectral fingerprints, the more the mystery deepened. The patterns of absorption lines suggested not just metals, but a distribution of temperatures consistent with a layered stellar population. Young stars, middle-aged stars, possibly even stars nearing the end of their lives. It was a hierarchy of ages that should have taken hundreds of millions, or even billions, of years to develop. Yet here it was, in a galaxy forming at a time when the universe itself was still in its infancy, still forming its first shapes. Imagine finding the ruins of a fully developed civilization buried beneath layers of rock dated to a time when humans were not even supposed to exist. The shock would be cultural, philosophical, existential. That was the level of shock astronomers felt staring at the spectral data. This wasn't merely unusual. It was a violation of cosmic chronology. There was another detail that sent chills through the team: the faint glow of ionized gases. Ionization required strong radiation sources, typically from massive, hot stars or clusters that had been active for extended periods. But these gases were arranged in a way that suggested stability and recycling, not the chaotic blowouts expected in early star-forming regions. Instead of a violent starburst tearing the galaxy apart, the distribution looked controlled, almost gentle, as if the galaxy had the time and environment to refine itself. But the young universe should have been far too hostile for that kind of refinement. Some astronomers described the chemistry as whispering secrets the universe was not ready to share. Others said it looked like the light from a galaxy that had lived a long life and then been teleported backward in time. One researcher joked darkly, "Either our models are wrong, or this galaxy is cheating." But the chemistry wasn't done shocking them. When the spectrum was pushed through more advanced modeling, it hinted at something even stranger: the possible presence of dust. Cosmic dust is made from the debris of dying stars. Seeing dust this early was like finding soot from a campfire before anyone had learned how to make fire. It shouldn't be there. It couldn't be there. And yet the spectral dips at certain wavelengths suggested its subtle, silent presence. Dust means death. Dust means maturity. Dust means cycles, not beginnings. The early universe was thought to be too hot, too violent, too young for dust to survive. But this galaxy's chemical signature hinted that dust had not only formed here but persisted. It meant stars had already lived, died, and enriched their surroundings. It meant time had passed, more time than cosmology allows. As the team analyzed deeper layers of the spectrum, they noticed that the energy distribution didn't match the typical curve of a young star population. Instead, it resembled something closer to intermediate-age stellar groups. Radiative cooling patterns were too smooth, emission lines too balanced. Like a symphony rehearsed, not improvised. The strangest part was that every attempt to force the data to fit established models only made the discrepancy worse. Remove metals? The spectrum resisted. Remove dust? The model became unstable. Assume younger stars? Luminosity curves broke. Assume high temperatures? Chemical lines contradicted. The galaxy refused to fit any scenario that kept the universe's timeline intact. It was a chemical rebellion, a defiance written in ancient light. And it left astronomers with agonizing questions. How did metals appear so early? How did dust survive? How did stars evolve so quickly? And what force could have accelerated cosmic chemistry beyond known limits? For the first time, the scientists began to consider possibilities that reached beyond comfortable physics. Perhaps dark matter behaved differently in the early universe. Perhaps unknown particles influenced star formation. Perhaps gravity acted more strongly in primordial epochs. Or perhaps the universe experienced short, intense bursts of accelerated evolution, cosmic shortcuts we have never theorized. As the team pushed back from their screens, a profound silence fell over the room. The strange chemistry of ancient light had spoken. It told them something impossible had happened. And whatever that was, it was only the beginning. The deeper scientists probed into the structure of the tiny galaxy, the more bewildering its internal contents became. It wasn't only the chemical fingerprints that defied expectation, it was the very nature of the stars themselves. When JWST analyzed the galaxy's light at higher precision, astronomers noticed something startling. The energy patterns didn't align with the youthful, chaotic stars expected in an early universe object. Instead, they resembled the steady burn of more mature stellar populations. These were not the first-generation giants that should have dominated this epoch. These were stars with histories, stars shaped by time the universe did not yet have to offer. And then came the most shocking discovery: faint hints of heavy elements and enriched star populations, signs of what researchers began calling phantom stars, stars that should not exist at all by the universe's timeline. The term wasn't official, of course. It began as a nervous joke exchange between two physicists, a desperate attempt to soften the blow of the data. Yet the name stuck because nothing else captured the sheer absurdity of what they were seeing. These phantom stars didn't belong to their era. They shone with the spectral characteristics of stars that had undergone long cycles of nuclear fusion. Some even hinted at remnants of earlier generations, stars born from the ashes of predecessors that, by all accounts, could not possibly have existed yet. To form heavy elements such as carbon, oxygen, magnesium, or iron, ancient stars must have lived their full life cycles, exploded as supernovae and enriched their surroundings. That process requires hundreds of millions of years of cosmic evolution. But here, in this tiny, compressed galaxy from the universe's earliest dawn, the signatures were already present. It was as if stellar generations had unfolded in fast forward, skipping the long, slow steps cosmology is built upon. This defied everything. The galaxy's metallicity levels were subtle, faint lines, slight deviations, but unmistakable. When scientists traced them back to the energy output and star formation rates, the only logical conclusion was that these stars had aged far too quickly. Or rather, they appeared to have aged. The patterns suggested stars with intermediate mass and temperature distributions, with some even displaying the dim glow characteristic of post-main sequence phases. This should be impossible. Stellar evolution is bound by physics, not preference. It cannot be rushed, unless something unknown was influencing it. Another anomaly emerged when researchers studied the brightness of specific stellar clusters inside the galaxy. They were too bright in some spectra, too dim in others, almost as if hidden populations of stars were lurking beneath the visible ones, ghost-like and silent. This was where the second shocking phrase emerged: impossible metals. The term referred to the spectral hints of elements that should not have existed this early, metals requiring multiple generations of star death and rebirth. These metals weren't abundant, but their presence was undeniable. They suggested that something had accelerated stellar evolution or that some unknown process had forged heavy elements far sooner than predicted. But how? One theory proposed that these stars formed from exceptionally dense gas clouds enriched by exotic particles from the early universe. Another suggested that primordial dark matter clumps may have ignited rapid star formation at unprecedented speeds. A third, whispered only in private conversations, hinted at the possibility that these stars were not native to the early universe at all, that they came from some unknown astrophysical event or timeline folded into the early cosmos. The very phrase impossible metals sent shivers through the scientific community. It meant nature had found a shortcut, a cosmic loophole, a way to produce complexity long before complexity was allowed. As JWST continued collecting data, the contradictions multiplied. The galaxy's stellar luminosity curve, its distribution of brightness across frequencies, showed signs of older stellar remnants. Some readings hinted at what could be the faint glow of white dwarf precursors. But white dwarfs require billions of years to form. This galaxy existed when the universe was barely a few 100 million years old. The timeline simply could not accommodate them. Yet the signals persisted. Some researchers scrambled to find errors. Maybe the galaxy was closer than it appeared. Maybe redshift measurements were distorted. Maybe gravitational lensing was magnifying and altering the signatures. But none of these explanations held up. The data was clean, consistent, and verified independently. One astrophysicist, exhausted after running the same simulations for the 10th time, muttered, "We're looking at ghosts." Another replied, "Ghosts don't leave spectral lines." Yet the lines remained, etched in ancient light. The discovery raised disturbing questions. Were these truly stars behaving impossibly fast? Or was something more exotic at play? Could these signals be remnants of an earlier universe, a previous cosmic cycle? Could the Big Bang's aftermath have allowed pockets of matter to evolve differently, forming microenvironments where physics operated at accelerated rates? The idea sounded like science fiction, yet the data refused to behave like science as usual. The galaxy's dense structure only amplified the mystery. Its stars were packed tightly together, closer than those in normal galaxies. This density suggested rapid gravitational collapse, far faster than current models permit. Such an environment could, in theory, accelerate star formation, but not to this extent. Not enough to explain metals. Not enough to explain phantom stars. Not enough to justify the seemingly ancient light radiating from a place that should have been only beginning to form structure. The more scientists examined the galaxy, the more it felt like a puzzle built from the wrong pieces. Pieces borrowed from different eras of cosmic history and forced together into a shape that made no sense. It was as though the universe had momentarily ignored its own rules and allowed a pocket of accelerated evolution to unfold. A glitch in reality. A cosmic error. Or perhaps something more deliberate. Some theorists, hesitant, cautious, almost embarrassed, raised the possibility of unknown astrophysical mechanisms, processes so fundamental yet so overlooked that their existence had gone undetected until now. Others speculated about interactions between dark matter and baryonic matter that could trigger runaway star formation. A few dared to suggest more radical ideas, strange early black holes influencing evolution, or quantum fluctuations on cosmic scales shaping matter in ways we cannot yet imagine. Whatever the explanation, one thing was certain. The phantom stars and impossible metals inside this tiny galaxy were not mistakes. They were real. They were ancient-looking. And they should not exist. The discovery left scientists with a chilling realization. If stars can appear older than their universe, if metals can form before the timeline allows, if galaxies can evolve with supernatural efficiency, then the universe is hiding something profound, something beyond current physics. And this tiny galaxy, with its ghost stars and forbidden elements, is the first crack in the facade. The first clue that the cosmos may be far stranger, far older, or far more complex than humanity ever expected. The more deeply scientists studied the strange little galaxy, the more it seemed to pull away from the familiar categories of the cosmos. It was not behaving like anything expected in the early universe. It was too dense, too mature, too chemically enriched, too neatly organized. Every observation only pushed it further outside the boundaries of known galactic behavior. And so, reluctantly at first, astronomers began exploring a possibility that felt almost unsettling to consider. Maybe this wasn't a normal galaxy at all. Maybe it was something older, weirder, and far more primordial. A ghost galaxy, a relic from a cosmic era we do not yet understand. The idea began as a whisper. A quiet thought shared between two researchers staring at the spectral data far too long. What if it's not a galaxy in the traditional sense? One said. What if it's something else? In science, such statements are dangerous. They invite imagination into a space dominated by evidence. But imagination has always been the birthplace of breakthroughs, and the data was already breaking all the rules. The concept of a ghost galaxy wasn't meant literally, not at first. It was a metaphor for something ancient and unclassified, something not built through the usual pathways of cosmic evolution. A structure that didn't follow the conventional sequence of star birth, enrichment, and galaxy growth. Instead, it seemed frozen in time, like a fossil from a forgotten experiment the universe performed before settling into its current laws. Ghost galaxies had been theorized before, though never confirmed. Some physicists speculated that shortly after the Big Bang, exotic pockets of matter might have condensed in unusual ways, forming miniature structures ruled by physics slightly different from what we observe today. These structures may have survived as relics, faint, compact, and nearly impossible to detect. They would be too small to classify as early galaxies, too evolved to call primitive, and too strange to fit into any known model. They would drift through cosmic history like faint phantoms, their properties whispering secrets from eras that no longer exist. When JWST zoomed deeper into the tiny anomaly, the ghost hypothesis gained weight. The galaxy's density and compactness were extreme, so extreme that they resembled theoretical microhalos, predicted to form under unusual dark matter conditions. These halos could trap gas so efficiently that stars formed rapidly and in tightly packed clusters. But the process would be brief, chaotic, and incredibly rare. Such structures would burn bright, evolve fast, and then fade into obscurity, leaving behind dense, relic-like fossils. The tiny galaxy fit this profile disturbingly well. Its compact nature suggested a rapid collapse. Its mature stars suggested a burst of accelerated evolution. Its faint metals implied an early violent enrichment. And its small, ghost-like appearance matched predictions of relic structures that should, in theory, have disappeared billions of years ago. Yet here it was, visible, intact, and glowing softly across the void. Some scientists proposed an even stranger idea. Perhaps this object formed in a region where the earliest quantum fluctuations created extremely dense pockets of primordial matter. These pockets could have collapsed into miniature galaxies before the universe fully stabilized, forming structures that existed outside the normal timeline of cosmic evolution. In that scenario, this galaxy wasn't old in the traditional sense. It was primordial, formed under conditions long vanished. Others suggested that what we were seeing might be the stripped core of a once larger galaxy. In the early universe, chaotic collisions and violent gravitational interactions were common. A larger galaxy could have been torn apart, leaving behind only its densely packed core. Such a core would contain mature stars and metals while being tiny in size. But this explanation had problems. Nothing nearby seemed massive enough to strip it, and the galaxy's intact structure didn't show signs of violent disruption. Another hypothesis took a more exotic turn. Some cosmologists suggested that the object might represent a remnant of a pre-galactic clump, something that formed before cosmic reionization, surviving in the shadows of the universe's darkest ages. This would make it a transitional object, a fossil bridging the gap between the earliest matter formations and the first true galaxies. These fossils were predicted but never observed. Seeing one would be like finding a prehistoric creature alive today, its existence rewriting evolutionary history. The more theories emerged, the more the galaxy felt like a ghost, haunting the boundaries of scientific understanding, refusing classification, drifting between categories as if it existed in a liminal space between realities. But the most haunting idea came from a small group of theoretical physicists who dared to push the concept even further. They suggested that this could be a structure formed by unknown physics, perhaps an early universe phase transition, or the collapse of exotic dark matter not yet discovered. In such a scenario, the galaxy wasn't just ancient, it was alien to our laws of formation. It belonged to a different cosmic rulebook, a different blueprint of creation, a different physics entirely. If true, this would mean the early universe was a place of astonishing diversity, a cosmic laboratory where multiple kinds of structures formed, some obeying the physics we know, others obeying rules we have not yet unearthed. Most of these experimental structures would have vanished. But some, perhaps only a handful, might still linger like ghosts, preserved relics drifting through time. The tiny galaxy may be one of them. As the scientists examined the data, they began to sense something humbling, even eerie. This structure did not evolve alongside the rest of the universe. It felt like something out of sync, an echo, a relic, a surviving artifact from a chapter of cosmic history no longer accessible. A ghost galaxy. Not supernatural but profoundly unnatural in terms of known physics. A reminder that the universe once experimented with possibilities that modern science has never imagined. And this small, stubborn anomaly shining across the void carried a message older than galaxies, older than stars, older than time itself. The universe's past is stranger than its present. And some remnants of that strangeness are still out there, waiting to be found. In every model of cosmic evolution, dark matter plays the silent, invisible role of the architect. It doesn't glow, it doesn't burn, it doesn't collide, but it shapes everything. Galaxies form because dark matter gathers into vast halos, pulling regular matter into deep gravitational wells. Stars ignite only because dark matter scaffolds give the universe its structure. And yet dark matter is something humans have never seen, only inferred. It is a shadow, an unseen force that outweighs normal matter by a factor of 5. Science relies on its predictable behavior, cold, passive, steady, and stable. But the tiny, impossible galaxy discovered by JWST threatens that stability. Its density, maturity, and improbable formation timeline cannot be explained by ordinary dark matter behavior. And so astronomers began to consider a radical possibility, one that feels as chilling as it is revolutionary. What if the dark matter around this galaxy misbehaved? The idea sounds strange. Dark matter isn't supposed to behave at all. It has no charge, no interaction with light, no friction. It merely exists as a gravitational ghost. But in the early universe, when temperatures were extreme, densities peaked, and physics danced at the edge of chaos, dark matter could have acted differently. Some theories already hinted that under certain conditions, dark matter might clump rapidly or collapse unusually fast. Others suggested it could self-interact or form dense knots known as dark stars, which could act as engines for accelerated galaxy growth. And when scientists compared these theories to the JWST data, something unsettling happened. The numbers lined up. The galaxy was far too small, far too condensed, and far too ancient in behavior to match any known model of baryonic, normal, matter evolution. But if dark matter had collapsed much more aggressively than expected, creating extremely dense gravitational wells, it could have pulled gas inward at incredible speeds. That gas could have ignited into stars far faster than normal physics allows. An early dark matter-driven collapse could explain the tiny galaxy's unusual maturity, its phantom stars, its impossible metals, its compact shape. This brought researchers to the first shocking hypothesis: exotic dark matter. According to this idea, the galaxy formed inside a halo of dark matter unlike anything seen before. Perhaps a type of dark matter that could cool, clump, or collapse in ways unknown to conventional theory. Some versions of this idea proposed that dark matter interacted with itself, forming dense cores that compressed normal matter with unprecedented efficiency. Others suggested a form of warm, or ultralight dark matter that could fragment the early universe into pockets of rapid collapse. If that were true, the early cosmos wasn't uniform. It was a mosaic, some regions evolving slowly, others exploding with accelerated structure formation triggered by exotic dark matter. But this hypothesis led to an even stranger possibility. What if the dark matter didn't just misbehave? What if it created stars? A controversial theory suggests that in the earliest eras, dark matter could have interacted enough with regular matter to release small amounts of heat. This could form objects called dark stars, not made of dark matter but powered by it. These stars would live long, grow massive, and forge heavy elements far sooner than normal stars could. If even a few dark stars existed in the region where the tiny galaxy formed, they could explain the enriched chemistry seen in its spectrum. Some theorists even proposed that the galaxy itself might be a remnant of a dark matter-dominated formation event, something that happened before the universe stabilized into the physics we see today. But then came the boldest hypothesis of all, an early collapse cascade. This idea suggested that dark matter halos in the very young universe may have entered a rapid chain reaction of collapse, pulling gas inward so violently that the galaxy's stars formed in a single, intense burst. It would be like watching an entire city rise in just a few days rather than over centuries. The tiny galaxy's density, maturity, and strange chemistry would be a natural consequence of this runaway gravitational collapse. If true, this meant the universe's early structure was far more chaotic than expected. Dark matter wasn't quietly shaping galaxies. It was driving them, accelerating them, and creating islands of rapid evolution. But this theory raised disturbing questions. Why would dark matter behave this way only in certain regions? Why did this galaxy and not others form through these exotic processes? Did something trigger the collapse? An early cosmic phase transition, a fluctuation, or something even stranger? As scientists explored simulations, something eerie emerged. In rare cases, very rare cases, dark matter halos could collapse into ultradense cores that form galaxies exactly like the one JWST detected. These models predicted tiny, ghost-like galaxies appearing at impossible ages, with mature stars and enriched chemistry. They were called dark relics. Structures born from the universe's deepest, oldest gravitational wells. Structures forged by dark matter acting under extreme primordial conditions. Structures that survive as fossils from an era before galaxies were supposed to exist. The tiny galaxy matched these simulations alarmingly well. If the dark relic hypothesis was correct, it would mean one thing. The early universe was full of processes humanity has not yet even begun to understand. Dark matter wasn't simply a cosmic skeleton. It was an active participant, shaping the first structures with hidden, unknown physics. But the implications didn't stop there. If dark matter misbehaved once, could it misbehave again? Could there be more relics hiding in the darkness? Could entire galaxies exist that were formed through mechanisms outside our physics? The tiny galaxy becomes more than an anomaly, more than a curiosity. It becomes evidence. Evidence that the universe might contain forces we have yet to imagine, hidden within the invisible substance that makes up most of its mass. And the universe, through this small, ancient whisper of starlight, offers humanity a profound message. Dark matter is not what we think it is. It may have shaped the cosmos in ways we've never considered. And its secrets, still buried in the shadows, are just beginning to surface. From the moment astronomers realized the tiny galaxy did not fit into any established model, an uncomfortable ripple spread across the scientific community. At first, it was just a whisper, an unspoken suspicion tucked behind cautious analysis. But as data accumulated, as contradictions sharpened, as every attempt to explain the anomaly collapsed under scrutiny, that whisper grew louder. It became a murmur, then a debate, then a confrontation with a possibility so destabilizing that many resisted saying it out loud. What if the foundations of the Big Bang model were incomplete? What if the universe did not evolve in the orderly, predictable way scientists believed? What if the cosmic story humanity had written was missing entire chapters? The discovery was not merely a challenge to one equation or one assumption. It was a crack running straight through the central pillars of modern cosmology. The Big Bang model is more than a theory. It is the backbone of astrophysics, the framework that explains cosmic microwave background radiation, galaxy distribution, element formation, and the expansion of space. It is the story of how everything came to be. But for the story to hold, The early universe must behave in certain ways. It must be young when it is young, unstable when it is unstable, and incapable of forming complex structures until long after the cosmic dawn. The tiny galaxy broke all of those rules. It was too mature, too chemically rich, too dense, too organized, too old for its time. And so scientists were forced to confront the terrifying truth. The anomaly wasn't just an anomaly. It was a direct challenge to the timeline of the universe itself. Some researchers clung to the hope that the redshift was wrong. Maybe the galaxy wasn't as far away, or as early as it seemed. But Webb's data was precise to an unforgiving degree. The light had traveled for over 13 billion years. The universe at that moment was still a child. Yet the galaxy looked like it belonged to a much older cosmos. If the age is right, the Big Bang timeline is wrong. If the galaxy is real, the model is incomplete. This forced scientists to revisit questions once settled. How fast did the first stars form? How quickly did matter collapse? How much time was really needed for heavy elements to appear? What if the universe evolved faster than predicted, or in a fundamentally different way? These questions were uncomfortable because they threatened decades of careful, painstaking research. But they could no longer be dismissed. And as more astronomers joined the investigation, competing ideas began to emerge, each one more daring, more unsettling than the last. One group proposed that the early universe experienced rapid structure bursts, short periods of accelerated gravitational collapse driven by unknown forces. In this scenario, galaxies could form far earlier and evolve far faster than expected. The tiny galaxy was not an outlier, it was evidence of a hidden phase of cosmic evolution. Another group revisited inflation theory, the idea that the universe expanded faster than light moments after the Big Bang. Some theorists speculated inflation may have created pockets of extreme density that evolved differently from the rest of the cosmos. These pockets could produce galaxies that look impossibly old. The tiny galaxy could be a survivor of one such pocket, an artifact of uneven cosmic birth. A more radical group considered modifying the laws of physics. Maybe gravity behaved differently in the earliest ages. Maybe particle interactions changed. Maybe dark matter and energy played roles that no one has yet imagined. Such ideas felt like rewriting the rulebook, not just adding a new chapter but changing the entire plot. Others took an even more controversial stance. Maybe the universe is older than we think. This would imply the Big Bang timeline is off, not by millions of years but by billions. It would mean models estimating the universe's age at 13.8 billion years are fundamentally flawed. If the universe were older, perhaps 20 billion years or more, then the tiny galaxy wouldn't be impossible. It would simply be ancient. But this idea creates new conflicts. Background radiation measurements, expansion models, and elemental abundances all align with a younger universe. Changing one value would domino into contradictions elsewhere. Cosmology is a delicate web. Tug on one thread and the entire structure trembles. Yet the galaxy demanded explanation. And so, despite resistance, a small but growing number of scientists began to ask the forbidden question. Is the Big Bang model wrong, or just incomplete? This was not the first time such doubts surfaced. Throughout history, cosmic discoveries have forced paradigm shifts. Heliocentrism replacing geocentrism, relativity replacing classical mechanics, quantum mechanics shattering determinism. Each shift felt impossible until evidence made it undeniable. Now, this tiny galaxy, compact, mature, chemically enriched, was doing the same. Some researchers described their experience emotionally. One astrophysicist said, "It feels like the universe is laughing at us." Another said, "We built such a beautiful model. I didn't expect the universe to break it this quickly." Gradually, the scientific community split into camps. The conservatives argued for caution. Maybe the galaxy is an illusion. Maybe rare processes explain it. Maybe everything is fine. The radicals argued for revolution. This is evidence of new physics. Evidence of new cosmic phases. Evidence that the Big Bang timeline is incomplete. The moderates stood in the middle, quietly terrified. They knew the truth. Astronomy is entering a new era. An era where Webb will reveal more anomalies, more contradictions, more impossible galaxies. If one such galaxy exists, there are likely hundreds waiting to be discovered. The pressure grew not just scientifically but philosophically. Because if the universe evolved differently, if the rules changed in the early cosmos, if structures formed faster than physics allows, then humans are standing on the edge of a profound shift in understanding. The tiny galaxy becomes more than a discovery. It becomes a messenger, a warning, a crack in the cosmic wall. The Big Bang model is not collapsing, but it is trembling, And the universe, through this impossible structure, whispers, "You do not yet understand me." The idea first surfaced in hushed conversations, half-formed thoughts exchanged in dim offices and late-night emails. No one wanted to bring it up publicly. No one wanted to attach their name to it. The topic was too controversial, too ridiculed, too often hijacked by fringe speculation. But as the impossible galaxy continued to defy every law, every timeline, every model, a few scientists reluctantly faced a possibility they hoped they'd never have to consider again. What if the universe is behaving like a programmed system? What if this anomaly is not just a glitch in our understanding, but a glitch in reality itself? The simulation hypothesis, a concept once relegated to philosophical debates, stirred uneasily back into the scientific arena. At first it was only a metaphor, a way for researchers to express the absurdity of what they were seeing. But metaphors sometimes have the unsettling habit of brushing against truth. And the tiny galaxy's existence eerily mirrored the sort of rendering error or timeline inconsistency that appears in digital simulations. The more the team discussed the anomaly, the more certain patterns began to resemble computational behavior. For instance, the galaxy was too mature for its time, like an asset loaded before the rest of the environment finished rendering. The heavy elements seemed to appear before the physics allowed, like skipped steps in a simulation shortcut process. The density and structure were too perfect, like compressed data packed into an early frame. These comparisons were not conclusions, of course, but the parallels were disturbing enough that scientists could no longer dismiss them entirely. Some researchers hinted at a deeper, more provocative interpretation. The universe might not be running on smooth, continuous laws. Instead, it could operate on discrete processes, quantized steps, algorithmic transitions, or computational shortcuts invisible to human perception. In such a universe, early cosmic structures might emerge inconsistently, with certain regions initialized differently from others. The impossible galaxy could be an initialization artifact, a structure loaded into the cosmic simulation with properties out of sync with its surroundings. In a simulation, environments are often rendered in layers. Key objects are loaded first, details filled in later. If the universe operates similarly, then the tiny galaxy could be evidence that ancient structures were generated rapidly, using rules not applied uniformly elsewhere. Other scientists took a more philosophical stance. They argued that if the cosmos is simulated, then anomalies are not failures, they are messages, indicators, hints left behind intentionally or unintentionally by the system's architecture. The galaxy felt like such a hint. Its maturity contradicted physics not by small margins but by staggering leaps. Its chemistry, density, and structure weren't simply anomalies, they were errors so bold, so dramatic, that they almost felt like the universe was waving a flag saying, "Look closer." One theoretical physicist described it elegantly: "It's as if the universe forgot to hide the seams." But the simulation hypothesis brought with it a cascade of existential questions. If the universe is simulated, who built it? Why does it exist? Who or what is running it? Is the simulation perfect, or full of overlooked imperfections? Are anomalies like this galaxy rare accidents, or intentional breadcrumbs? The galaxy forced these questions into uncomfortable proximity with evidence. One subset of researchers proposed a radical interpretation. The universe might periodically update, with physics shifting subtly during different epochs. If this object formed during an earlier version of cosmic physics, then its properties could reflect rules that no longer apply today. This would explain why it appears older than allowed and contains impossible metals. In a simulation, updates cause legacy artifacts. Old objects sometimes persist under new rules. This galaxy could be one. Another group suggested a different perspective. Perhaps the universe optimizes computational load by simulating only what needs to be observed. When JWST peered deeply into an unrendered region, the simulation might have generated a placeholder galaxy. One built too quickly, incorrectly, without the correct historical constraints. The object would then be an artifact of emergent resolution, a cosmic texture loaded inaccurately. This idea felt wild, even absurd. And yet, the galaxy's properties remained equally absurd. As the discussion grew, so did the philosophical tension. The simulation hypothesis offers explanations not because it is correct, but because the anomaly pushes scientists into conceptual corners where traditional physics feels increasingly insufficient. And that is what unsettles them most. If the universe is simulated, then anomalies are not mysteries to solve. They are reminders of the system's limitations. If the anomaly is real, then the simulation argument gains weight. If the universe is not simulated, then the anomaly points to physics we do not yet understand. Both possibilities are equally frightening. Some researchers dismissed the idea with frustration. Others entertained it quietly. A few embraced it openly, arguing that the galaxy might be the strongest evidence yet for a computational cosmos. Regardless of their stance, one truth remained: the discovery had reopened a philosophical door long bolted shut. The universe suddenly felt less like an elegant physical system and more like a coded environment, full of patches, irregularities and oddities lurking beneath the surface. And as scientists stared at the impossible galaxy glowing across billions of years, they could not escape a chilling thought: if this is a simulation, what else might be waiting to reveal the structure of the code behind reality? The deeper scientists ventured into the enigma of the tiny galaxy, the more their confidence in conventional explanations eroded. What began as a curious anomaly had evolved into a cosmic confrontation, one that forced astronomers to ask questions they had long avoided. For decades, astrophysics stood firmly on the foundations of natural processes and predictable cosmic evolution. Yet this galaxy, impossibly old and impossibly structured, pushed some researchers into a dangerous intellectual territory, the realm where natural and unnatural blur together. Most scientists rejected extraordinary interpretations at first. They were hesitant, cautious, bound by the discipline of evidence. Still, the data refused to bend. Metals that shouldn't exist. Stellar populations that required time the universe didn't have. Structures that looked engineered rather than chaotic. The galaxy behaved not like a typical child of cosmic forces, but like something curated, designed, composed. The philosophical implications hung heavy in the background, quiet, unspoken, unsettling. Could this galaxy be evidence of ancient, unknown civilizations? Or was it simply an exotic natural object so rare and extreme that it mimicked the characteristics of something artificial? The question alone was taboo. Scientists who voiced it risked professional backlash. Yet the galaxy's properties were so extraordinary that even the most grounded researchers found themselves drifting into speculative waters. Some began with the natural possibilities. Perhaps the galaxy represented an exotic astrophysical object, an early universe hypercluster formed through unusual gravitational conditions. Maybe dark matter halos created a rare pocket where star formation happened at unnatural speeds. Maybe quantum fields in that region triggered accelerated evolution. These explanations felt safer, aligned with known physics even if pushed to the edge. But none solved the entire puzzle. Every model left gaps, huge, gaping inconsistencies that refused to be filled with standard theory. And so the fringe question crept back in: could intelligence have played a role? Not human intelligence. Not biological intelligence as we know it. But the intelligence of something ancient. Something that might have risen so early in cosmic history that its existence would rewrite everything humans believe about life. At first, this theory focused not on intentional design but on remnants. Perhaps an ancient civilization once inhabited or influenced this galaxy, leaving behind structural or chemical signatures that persisted for billions of years. The idea seemed ridiculous. Life shouldn't have existed then. Planets shouldn't have formed. Chemistry shouldn't have been stable. Yet the galaxy's unusual metals and mature star clusters hinted at processes far too orderly for the era. One theorist argued that if advanced civilizations emerged in certain rare pockets, accelerated by exotic dark matter or early cosmic cycles, they could have lived and died long before typical galaxies formed. In that case, the tiny galaxy might be a graveyard, a fossilized remnant of a time when intelligence emerged under impossible conditions. Others went further. They suggested the galaxy might be an artifact, not a natural structure but a cosmic-scale relic created or altered by unknown beings. Megastructures spanning light years have been theorized before: Dyson spheres, star-lifting engines, stellar harvesters. But a galaxy-scale construct? That bordered on the unimaginable. And yet, the tiny galaxy's perfect compactness, its improbable density, its rapid enrichment, its unnatural maturity, its defiance of cosmic evolution. Some found themselves wondering, could this be the signature of a civilization that manipulated matter on galactic scales? Perhaps they used stars as tools. Perhaps they compressed matter deliberately. Perhaps they reshaped their environment in ways that mimic the accelerated evolution the data suggests. But this idea felt too extreme even for bold thinkers. So speculation shifted toward a more subtle possibility: the galaxy might be an accidental remnant of advanced activity. If early civilizations experimented with extreme physics, they might have triggered local accelerations in matter collapse, igniting premature star formation, generating metals early, leaving behind structures that look unnatural. Just as nuclear experiments leave isotopic fingerprints on Earth, celestial engineering might leave signatures detectable billions of years later. But the biggest question haunted every discussion. How could a civilization arise so early? The universe was young, chaotic, hostile. Stars were unstable. Planets were rare. Chemistry was primitive. Everything argued against life. And yet the galaxy's advanced features argued against natural evolution. So a small group of theorists proposed a different possibility, that life did not originate here but migrated here. Maybe civilizations from older cosmic cycles, universes before this one, left behind artifacts. Maybe they seeded early galaxies with engineered matter. Maybe they survived cosmic collapse through means incomprehensible to human science. This idea aligned with certain speculative cosmological models in which universes evolve in cycles, transferring information or matter across cosmic rebirths. In that case, the tiny galaxy could be a seed from a past universe, a relic from before the Big Bang, carrying materials, structures, or technologies predating the very physics scientists used to judge it. Others suggested a more grounded but equally eerie interpretation. Perhaps this galaxy is simply a natural oddity, an extreme outlier produced by rare combinations of gravitational fields, quantum fluctuations, and primordial dynamics. Nature, after all, is a master of strange outcomes. Sometimes the universe produces phenomena that look intentional but are purely coincidental. Yet even this explanation felt insufficient. Because the galaxy was not just strange, it was coherent. Not just rare but structured. Not just early but prematurely ancient. It looked like the universe had attempted something ambitious in its infancy, and succeeded too well. And so the debate continues, is this the fingerprint of ancient intelligence? A relic of a forgotten cosmic age? A bizarre but natural accident? Or something in between, something that challenges the very boundary between natural and artificial? Regardless of the interpretation, one truth holds. This tiny galaxy forces humanity to confront the limits of imagination. It pushes science to its philosophical edge. It whispers of possibilities too vast, too ancient, too uncanny to ignore. Whether it is a cosmic artifact or a natural miracle, it stands as a reminder that the universe is not simply a collection of physical laws. It is a realm of mystery, shadowed history, and uncharted potential. And somewhere in that darkness, this tiny anomaly waits, silent, enigmatic, and daring us to uncover what it truly is. The deeper scientists journeyed into the mystery of the tiny, impossible galaxy, the clearer one truth became. This was not simply an anomaly. This was a window, an opening into an older, stranger universe, one whose evolutionary story might be far more complex than the clean, orderly sequence outlined in textbooks. As theories collapsed and models faltered, a new wave of thinkers emerged. Those willing to consider that the universe itself might have evolved through processes humanity had not even begun to imagine. This galaxy was not just breaking rules, it was hinting at hidden ones. To understand what might have happened, cosmologists revisited the earliest moments after the Big Bang, searching for overlooked possibilities. The conventional story portrays the early universe as uniform and predictable, a smooth sea of hydrogen and helium slowly forming stars, then galaxies, then clusters. But cutting-edge simulations suggested a very different picture. One in which the universe behaved like a wild experiment, full of short-lived phases, exotic states of matter, and bursts of accelerated structure growth that mainstream models smooth over. Perhaps, they proposed, the early cosmos was not a calm beginning but a rapid, chaotic evolution. One with secret chapters of development long erased from cosmic memory. One emerging idea was that the universe might have undergone hidden evolutionary phases, short bursts where physical laws temporarily shifted or additional forces behaved differently. In these phases, matter could condense faster, gravity could operate more efficiently, and star formation could ignite almost explosively. If the tiny galaxy formed during such a window, its impossible maturity would make perfect sense. It would not be a violation of physics, but an artifact of physics in a different state. This concept found support in studies of early cosmic inflation. Inflation wasn't a smooth expansion. It was turbulent, uneven, fragmented into patches of varying density. Some of those patches may have cooled faster. Others may have experienced quantum fluctuations that triggered early collapse. Still others may have inherited exotic field values that altered gravitational strength or sped up matter condensation. These regions, known as primordial islands, would evolve differently from the rest of the universe, faster, more aggressively, more efficiently. This tiny galaxy may be the first evidence of one of those islands. Other theories explored the possibility of rapid early starburst epochs, where conditions briefly favored intense, accelerated creation. In certain rare pockets, gas clouds could have cooled unusually fast, triggering a runaway chain reaction of star birth and enrichment. In these regions, stellar life cycles could occur in compressed timescales, allowing multiple generations of stars to rise and fall far earlier than expected. Heavy elements would appear prematurely. Dust would form. Mature clusters would emerge long before the universe was supposed to allow them. The tiny galaxy's spectral signatures aligned disturbingly well with this scenario. Still, some scientists believed these explanations only scratched the surface. They argued the anomaly might reflect alternate paths of cosmic evolution, branching possibilities that never became mainstream but still occurred in isolated pockets. Perhaps the universe explored multiple evolutionary pathways simultaneously, like a vast biological ecosystem experimenting with different forms of life. Most pathways failed, collapsed, or merged into larger galaxies. But a few, like this tiny relic, survived, preserved as fossils of long-forgotten cosmic experiments. This led to a bold new idea. The universe might not have one universal timeline of evolution. It might have many. Different regions could evolve at different rates. Some quickly, some slowly, some constrained by conditions we do not yet grasp. The universe, in this interpretation, is not a synchronized system but a patchwork of local histories, each shaped by its own micro-conditions. In one region, galaxies took billions of years to form. In another, they snapped into existence in cosmic instants. This galaxy may embody a timeline that diverged from the rest of the universe, a hidden evolution running parallel to the standard one. Yet another group of theorists pushed deeper into the unknown. They proposed that the early universe might have possessed additional fields or forces that later decayed or vanished. If such forces existed, exotic gravitational states, temporary energy fields, or rapidly shifting particle ratios, they could have accelerated the growth of matter in specific regions. Once these conditions faded, the universe settled into its familiar physics, leaving behind relics like this galaxy as silent witnesses of an earlier cosmic era. One theoretician described it beautifully: perhaps the universe had a childhood full of wild, unpredictable growth spurts. This galaxy is a scar from that childhood. Others suggested that early black holes might have played a surprising role. If primordial black holes existed right after the Big Bang, their gravitational influence could have rapidly pulled gas into compact formations, igniting intense starbursts. These black holes, possibly formed from fluctuations in the earliest instance of creation, might have been the nuclei around which the first structures formed. Some could even have evaporated through Hawking radiation, leaving behind dense, star-rich remnants, like the tiny galaxy JWST observed. But the most profound theory, one gaining quiet momentum, suggested that cosmic evolution itself might be recursive. Perhaps the universe is not experiencing its first cycle of formation. Perhaps early galaxies inherited information or structures from previous cosmological epochs, echoes from older universes embedded within the fabric of spacetime. In such a scenario, this tiny galaxy might be a memory, a carryover structure from a lineage older than the Big Bang. It would not be old because it evolved early, it would be old because it never truly reset with the rest of the cosmos. This idea is speculative, controversial, and breathtaking, but the galaxy's characteristics fit the pattern. Whatever the explanation, one truth becomes undeniable: the universe is not a simple linear machine. It is a vast, ancient organism, growing, experimenting, evolving in ways humanity is only beginning to glimpse. The tiny galaxy discovered by JWST is not just an anomaly. It is a revelation. A whisper from a hidden past. A reminder that the cosmos may contain multiple histories, multiple timelines, and multiple pathways of creation. It tells us that the universe's evolution is deeper, richer, more mysterious than we ever imagined. And in its quiet, ancient glow lies a promise that we are standing at the very edge of a cosmic truth much larger than ourselves. A truth waiting to be uncovered in the shadows of the early universe. As the data grew clearer and the implications grew stranger, the scientists studying the tiny galaxy found themselves living through a rare moment in human history, one where the universe itself seemed to be speaking directly to them, challenging their understanding, daring them to think beyond the boundaries of established knowledge. And in the midst of that intellectual storm, something deeply human began to unfold: awe, fear, confusion, exhilaration, and a powerful sense of purpose. This wasn't just a scientific puzzle anymore. It was an emotional journey, one that pulled every researcher into the gravity of an ancient cosmic mystery. Initially, many responded with disbelief. The numbers looked wrong. The models failed. The spectral lines contradicted everything they had learned. It was easier, much easier, to suspect an error. A glitch. A miscalibration. Anything but a challenge to the universe's foundation. But as the evidence piled up, resistance gave way to an uneasy acceptance. The tiny galaxy was real. Its contradictions were real. And the team studying it found themselves wrestling with emotions they hadn't felt since childhood, when the night sky still held its raw, unfiltered magic. Some reacted with pure awe. For them, this discovery was a thrilling reminder that the cosmos still had surprises left, surprises big enough to shatter assumptions and rewrite cosmic history. These scientists spoke with wide eyes and breathless excitement. They felt lucky, privileged, to be alive at the moment when the universe revealed something impossible. To them, the galaxy wasn't a problem. It was a gift, a cosmic privilege few generations ever receive. Others reacted with fear. Quiet fear. Unspoken fear. The kind that doesn't come from danger, but from meaning. If this one galaxy contradicted the laws of evolution, what else might be wrong? What other certainties might collapse? These researchers felt like they were standing on thin ice, ice that had already begun to crack. They worried that massive revisions would ripple across cosmology, breaking cherished theories, undermining decades of work, forcing them to relearn the universe from the ground up. Fear, in this case, wasn't irrational. It was the natural response of scientists who realized they were staring at something so profound it threatened the intellectual scaffolding of their entire field. Some experienced both awe and fear simultaneously. They found themselves unable to separate the two, caught in a paradox as mesmerizing as the galaxy itself. In private journals, they wrote about feeling small, frighteningly small, yet connected to something immense. In quiet conversations, they confessed that this discovery made them question not only cosmic history but humanity's place in it. Were we truly ready for what Webb was revealing? Or had we opened a door too soon? For younger scientists, those new to the field, this discovery was an invitation to dream without limits. They entered astronomy expecting mystery, and this galaxy delivered mystery on a scale they had never imagined. They felt energized, electrified, eager to be part of the generation that would propose new theories, new models, new ways of thinking. They spoke with the boldness of youth, imagining futures in which this galaxy was the first of many, each one revealing more secrets of the early universe. Veteran scientists felt something else: humility. Many of them had built their careers on the standard model, teaching it, defending it, perfecting it. Seeing it challenged wasn't a defeat, it was a reminder that science is not about being right, but about confronting truth, even when truth is uncomfortable. Some spoke about feeling liberated. If the universe was forcing them to rethink everything, then perhaps they were being invited to participate in one of humanity's greatest intellectual revolutions. The emotional spectrum widened as JWST continued gathering data. Researchers who rarely expressed sentiment found themselves staring at images of the tiny galaxy late at night, feeling a strange connection, almost a sense of companionship, with a structure billions of years old. The galaxy became a symbol of endurance, a survivor of unimaginable cosmic conditions. It had crossed the entire history of the universe to reach them. Its ancient photons had traveled unbroken paths through collapsing stars, merging galaxies, and expanding space, all to arrive precisely now, at a moment when humanity finally possessed the technology to read them. The psychological impact of that realization was profound. Some scientists described the experience as spiritual, not in a religious sense but in the sense of encountering something bigger than comprehension. A reminder that the universe is not obligated to explain itself. A reminder that humans are tiny observers, granted the fragile privilege of glimpsing fragments of an incomprehensible cosmic narrative. Others found themselves driven by determination. They felt a responsibility, not just to science but to the future, to decode this mystery no matter how long it took. They worked long nights, skipped meals, attended meetings with tired eyes but sharpened focus. They combed through data again and again, searching for patterns, hints, anything that might lead to an explanation. Determination became their anchor amidst the expanding storm of questions. In laboratories and observatories around the world, collaboration surged. Scientists who had once been rivals joined forces. Teams from different nations pooled their expertise. The mystery transcended competition. It became a shared human quest. For a moment, the vastness of the universe united people whose lives had been devoted to studying it. They were no longer just astronomers, physicists, or theorists. They were explorers staring at a map that had suddenly grown larger, stranger, more beautiful than they had ever imagined. This was the human response, awe at the unknown, fear of the implications, wonder at the beauty, determination to understand, humility in the face of cosmic truth, and a quiet, growing acceptance that this tiny ancient galaxy was not just a scientific puzzle, it was a mirror reflecting the limits of human knowledge, a mirror reminding us that the universe is infinitely more complex than we dare assume, a mirror showing that even the smallest object can hold the power to reshape our understanding of everything. As this galaxy glowed softly across billions of light years, it ignited something equally powerful within the hearts of those who studied it. The realization that humanity is still at the very beginning of its cosmic journey. And the journey has only just begun. The galaxy first appeared as nothing more than a faint, trembling spark, barely a whisper of light lost in the vastness of cosmic darkness. Yet as JWST peeled back the layers of ancient time, this fragile glow began to reveal a message far larger than itself. What looked small, insignificant, almost ignorable from a distance emerged as one of the most powerful discoveries in the history of astronomy. This tiny galaxy, compact and quiet, carried within its soft radiance a truth capable of shaking the foundations of human understanding. A truth the universe had kept hidden for billions of years. At first, the message seemed simple. Something was wrong. The galaxy was too old, too dense, too mature. It behaved like an object from a later universe, not the young, chaotic era in which it appeared. But as scientists studied its spectral fingerprints, its ancient chemistry, its impossible density, a realization began to take shape. This galaxy was not merely breaking rules. It was speaking. It was telling a story older, stranger, and deeper than any cosmic narrative humanity had ever imagined. Every photon escaping from this tiny structure had been on a journey older than human civilization, older than Earth, older than the Sun. Those photons had crossed the entire history of the cosmos, supernovae, collisions, expansions, voids, cosmic storms, before finally falling into JWST's golden mirrors. And encoded within that journey was a single, profound message. The universe is not what we think it is. The galaxy's existence implied earlier star generations where none should exist, mature structures where chaos should reign, metals formed before time allowed, and gravitational behavior that defied known physics. It was as if the cosmos had left behind a breadcrumb, an ancient clue pointing toward chapters of reality still unread. This tiny galaxy was not merely an object. It was a statement, a challenge, a quiet rebellion against everything science believed about cosmic evolution. The deeper astronomers looked, the more poetic that message became. In its starlight was the memory of an era no living being had ever seen, an era where the universe might have evolved through forgotten phases, accelerated bursts, hidden forces, or even alternate rules. This miniature island of stars was not out of place. It was a survivor from a hidden history, a relic that slipped through cosmic time to remind humanity how little it truly knows. And in that reminder was something profoundly humbling. For centuries, humans assumed the universe was predictable, progressive, and linear. But this galaxy stood like a monument to uncertainty, proof that reality does not follow human expectations, that the cosmos creates beauty and complexity long before physics says it should, that even in the dawn of creation, the universe may have been experimenting, evolving, exploring possibilities that current theories cannot yet describe. To the scientists, this realization felt like hearing the universe breathe, as though the cosmos itself was saying, "You have only seen the surface. Look deeper." The structure of the galaxy, small yet powerful, fragile yet impossibly ancient, served as a metaphor for truth itself. The universe often hides its greatest revelations in the smallest corners, waiting for someone patient enough, curious enough, bold enough to find them. And now that humanity had finally developed the tools to see far enough, the universe was beginning to reveal what it had kept secret for billions of years. Its message was not chaotic or ominous. It was gentle, quiet, and filled with awe. It told of a cosmos more flexible than rigid, more mysterious than mapped, more alive than mechanical. A universe that evolves in layers, in hidden currents, in staggered timelines. A universe where one tiny galaxy could silently rewrite the story of creation. This galaxy was a reminder that the early universe was not simple, that the cosmos is not fully understood, that the grand narrative of existence is filled with missing pages, pages that discoveries like this one help restore. And as scientists stared into its ancient light, they felt as though they were being invited deeper into a cosmic dialogue. A dialogue that asked, what else lies hidden in the early universe? What secrets have not yet emerged from the darkness? What structures exist that defy everything we believe about time, formation, and matter? The tiny galaxy held no answers, only clues. No conclusions, only provocations. No certainty, only possibility. And in that possibility lay its true power. It taught humanity that understanding the universe is not about having all the answers. It is about embracing the mysteries that push us toward new questions. It reminded researchers that even the smallest relic can reshape the largest theories. As its soft, ancient glow traveled across the cosmos and reached human eyes, it carried with it a cosmic whisper. Reality is deeper than you know. Keep looking. A tiny galaxy with a giant message. One that echoes through the vastness of space and challenges the boundaries of human imagination. One that hints that the universe still holds countless secrets waiting for the next lens, the next mind, the next question to bring them to light. The discovery of the tiny, impossible galaxy didn't just rewrite scientific papers. It ignited a fire in the global astronomy community. As soon as JWST's data became public, every major observatory, every research group, every cosmology department in the world seemed to pause, look up, and collectively ask the same question. If this is what Webb found so early in its mission, what else is waiting in the darkness? This question didn't inspire fear this time, it inspired ambition. Scientists realized they were standing at the threshold of a new era. The first anomaly was shocking, yes, but it was only the beginning. From that moment forward, the mission evolved. JWST was no longer just a telescope observing ancient light. It became humanity's frontline explorer at the edge of the known universe. And the next steps, what comes next, promised to be even more transformative than the discoveries already made. The first wave of planned observations focuses on hunting for more anomalies. If one impossibly old, impossibly dense galaxy exists, the statistical odds suggest it cannot be alone. Galaxies form in clusters, families, threads across the cosmic web. If this tiny relic is a survivor of some hidden evolutionary phase, there may be dozens, maybe hundreds, waiting in the background, too faint for older telescopes to detect. JWST's NIRCam and MIRI instruments will continue deep field surveys, pushing exposure times longer than ever before. Some scientists believe that within a year, the telescope will uncover entire populations of prematurely formed galaxies, objects that should not exist, blinking into view like ghosts from a forgotten timeline. And each new anomaly will help map out where, when, and how the early universe behaved differently from our expectations. But Webb's mission doesn't stop at hunting anomalies. The real power comes from spectroscopy, decoding the chemistry, temperature, velocity, and age signatures embedded in ancient light. With spectroscopy, the next steps will reveal whether the galaxy contains multiple generations of stars, whether it formed around an exotic dark matter core, whether its metals originate from unknown stellar processes, whether it shows hints of early black holes or dark stars, whether its chemistry matches normal astrophysics, or breaks it. Every new observation deepens the investigation. Every photon Webb collects helps rebuild the hidden history of the cosmos, piece by ancient piece. Other space agencies are already preparing complementary missions. ESA, NASA, JAXA, and private organizations are discussing next-generation telescopes designed specifically to explore the anomalies Webb is finding, machines that will surpass JWST in precision, depth, and scope. Some will specialize in infrared, others in gravitational wave mapping, others in ultra-high-energy particle detection. Together, they will assemble a multi-sensory portrait of the early cosmos. Even more exciting is the prospect of gravitational lensing surveys. Massive galaxy clusters act as cosmic magnifying glasses, bending and amplifying distant light. As JWST continues mapping these natural lenses, astronomers expect to find magnified versions of early universe objects. Tiny galaxies blown up in clarity, revealing internal structures that would otherwise remain invisible. It's like nature is offering its own telescopes, boosting Webb's power exponentially. In the coming months, JWST will also target regions of the sky that have been suspiciously quiet. The darkness between bright galaxies, the voids that appear empty, the forgotten corners where faint light lingers. These are the places where now humanity expects to find relics. Not just galaxies, but perhaps early star clusters, orphaned black holes, primordial clouds, or structures that do not fit any known category. Each discovery will bring the universe's hidden past into sharper focus. And while some scientists are searching for more objects like the tiny galaxy, others are preparing to test the very physics that governs cosmic evolution. Observations will target changes in gravitational behavior at early epochs, unexpected interactions between dark matter and baryonic matter, possible early cosmic accelerations or microinflation pockets, signatures of exotic particle decay or clues of alternate cosmic cycles. In other words, The search for new physics begins now. The theoretical community is preparing too. New models are being drafted every week. Models that stretch beyond the standard cosmological framework. Some invoke modified gravity. Others propose early dark matter interactions. A few even suggest the universe experienced multiple overlapping evolutionary modes, where structure formed at different speeds in different regions. These theories will be tested with upcoming JWST campaigns. If confirmed, they could usher in a revolution in physics equal to Einstein's or quantum mechanics. But perhaps the most powerful development is psychological, not technological. For the first time in decades, cosmology feels open-ended again. The field no longer believes the biggest discoveries are behind us. Instead, scientists sense that the most transformative revelations are still ahead, hidden in the faintest starlight of the earliest era. The tiny galaxy has become a symbol of cosmic humility. It reminds humanity that the universe is bigger, stranger, and more ancient than our models allow. And its discovery has ignited a determination unlike anything seen since Hubble first revealed that the universe extended far beyond the Milky Way. JWST is no longer just a mission, it is a beginning. The next steps involve coordinated global campaigns, deeper exposures, targeted dark-field observations, and theoretical revolutions. Scientists will probe deeper, question harder, and look fearlessly into the unknown. Perhaps Webb will find more impossible galaxies. Perhaps it will find structures so strange we have no words for them. Perhaps it will reveal errors in our physics, or entirely new laws. Perhaps it will uncover relics from older cosmic cycles. Perhaps it will identify the very first star or the earliest black hole. Whatever comes next, one truth is clear. The universe is opening its ancient gates. And through the golden eye of JWST, humanity is stepping into a cosmic era of discovery that will redefine our understanding of existence itself. This tiny galaxy was the first message. The next discoveries will be the answers. The final question does not arrive suddenly. It grows, quietly, steadily, through each contradiction, each anomaly, each flicker of ancient light that JWST pulls from the cosmic abyss. By the time scientists finish analyzing the tiny, impossible galaxy, the question is already there, lingering in the back of every mind, waiting with a patience carved from billions of years. It is the question that rises when certainty collapses, when models fail, when the universe reveals something so profoundly out of place that it forces humanity to pause and look inward. The question does not belong to astronomy alone. It belongs to philosophy, to existence, to the very nature of being. For as long as humans have looked at the night sky, they have carried with them an unconscious belief that the universe is comprehensible, that with enough time, enough mathematics, enough telescopes, the cosmos will eventually make sense. It is a comforting assumption, one that allows humanity to approach the vast unknown with confidence. But the tiny galaxy shatters that confidence. It reveals a universe that does not merely hide secrets. It reveals a universe that may be fundamentally beyond understanding. And so, as scientists gather around screens glowing with the oldest light ever seen, the final question forms. What does it mean when the universe disobeys its own rules? This question is not technical. It is existential. It asks whether the universe humans have mapped is only a fragment of a larger, hidden reality. It asks whether cosmic evolution is linear or layered, singular or multiplied, simple or staggeringly complex. It asks whether humanity's place in the cosmos is far smaller, or far more significant, than anyone realized. The galaxy has already proven that the early universe behaved differently than predicted. It has already shown that matter formed earlier, faster, and more efficiently than physics allows. It has already demonstrated that cosmic history may be nonlinear, that the universe may carry scars or relics from forgotten eras. But underneath all these scientific implications lies something deeper, something personal. If the universe still holds secrets this enormous, what else remains undiscovered? What else lies behind the veil of cosmic time? What else challenges our definitions of possibility? What else in the cosmos exists that humanity has not even imagined? The tiny galaxy is a reminder that knowledge is not a destination. It is a horizon that recedes each time we approach it. It invites humanity to abandon the illusion of mastery and embrace a larger, more humbling truth. The universe is not obligated to be simple or convenient or comprehensible. It is vast. It is ancient. It is layered with mysteries so profound that even our most powerful telescopes can barely scratch the surface. And yet, this realization does not diminish humanity. It elevates us, because the universe did not hide this galaxy forever. It waited until humans built a machine capable of seeing it. It waited until curiosity, determination, and imagination converged into a golden eye drifting through space. It waited until humanity was ready, not to understand fully but to begin understanding. The final question whispers through the silence of deep space as JWST stares into the abyss. If one tiny galaxy can overturn everything we know, what else lies out there waiting to be found? It is a question that fuels discovery. A question that humbles and inspires. A question that suggests the universe is not a closed book, but an endless manuscript still being written. And as the camera of the documentary pulls away from the tiny, impossible galaxy, its faint glow shimmering against the infinite black, the narration offers the final, haunting thought. Maybe the universe is not asking us to solve it. Maybe it is asking us to keep searching. Because the greatest mysteries are not the ones we understand, but the ones that change us simply by being discovered. And so humanity stands beneath the vast cosmic canopy, staring up through the golden eye of JWST, carrying one last question into the darkness. What else shouldn't exist, but does?